Good day and welcome everyone. So today what we're going to be doing is what is called the Bohr Light Demo Lab. And so we're talking about the electromagnetic spectrum, and electromagnetic spectrum is different forms of radiation, and there are specifically 7 different forms of radiation. So we're going to go over those different forms, and I have a saying for those different forms, so we're going to write it actually right on top of the screen here. So the saying is, run, Mark, it's Vicky, your ex-girlfriend. Okay, so everybody's going to say it with me. So say, run, Mark, run, Mark, it's Vicky, it's Vicky, your ex-girlfriend, your ex-girlfriend. Okay, now, what the different types of radiation are, the 7 of them, and we are going to do them in order of run, Mark, it's Vicky, your ex-girlfriend are, so we're going to say radio waves, microwaves, say it. Radio waves, microwaves. Then we've got infrared, visible. Infrared, visible. Now with visible light, this visible light right here, you probably know a guy's name that are the color of the rainbow. What are they? Do you guys know the guy's name? His name is Roy something. Roy G. Biv. His name is Roy G. Biv. And so what are these colors? Red, orange, yellow, green, blue, and violet. Okay, now after violet is this U one. Does anybody know what the U is? Ultraviolet. So there's violet and then there's ultraviolet. Before red is called, do you guys remember what the I was for? Infrared. So before red is infrared, and then visible light actually splits up here. And so this is going in order. And so after ultraviolet, then comes what? What do you think the X is for? X-rays, and the G is for gamma rays. Okay, now, these waves right here are actually going to be really long waves, but with the low frequency. When we get to gamma waves, these are going to have a really high frequency, and they're going to be high energy and high frequency, but their wavelength is going to be a lot shorter. So as we go from radio waves across to gamma, they actually become much more energetic and much more penetrating and much more damaging. So which wave do you not want to be around? A gamma wave, okay? Gamma waves are going to destroy and mutate cells, and if they start to replicate, then that could be cancer, for example, or you could completely be disintegrated, okay? So what we're going to be focusing on is seeing visible light, okay? And the cool thing is the colors here also go in the same direction. So it's basically like we take the visible light and we split it up also according to frequency. So as we get to this end, we have high energy, we have high frequency, but do you remember what was the opposite of those? What was inversely related? Wavelength, beautiful. The wavelength was actually going to be low. But on the other side, it's the opposite. The radio waves are lower energy, they have a lower frequency, but their wavelengths are, yep, they're longer. Perfect. They're going to be longer, which is the opposite. Okay. So when you do red, for example, versus violet, violet is actually a higher energy or a higher frequency. So red is going to be a much, what? What do you think? Lower or higher frequency then? Lower. Lower frequency and lower energy, but then it'll have a longer wavelength than the violet does. Okay. So when you see a rainbow, and a lot of people will ask, like, how is it that I see a rainbow? How do I see the different colors? So what we're going to do is we're going to take a look through these glasses here. And so these are diffraction gratings. You can't see it, but these have little teeny tiny slits in them, and that's separating the light. So if we can, we're going to try to split the light and be able to see that. And so if you can get the way that the wavelengths hit our eyes is what gives us different colors, okay? So they bounce and they hit, and then it gives us a different color. So you might see red depending on a frequency, and we were talking about, last hour, we were talking a little bit about the different colored, the dresses, for example, where some people see a white and gold, and some people will see a black and blue dress. And so there are some cool things that we can talk about as far as like the way that our eyes work and the way that wavelengths hit, okay? So a rainbow is seen when white light from the sun is refracted or bent as it passes through water droplets. So white light from the sun is, they use this word refracted or bent, and it's going to pass through the water droplets. And so we're going to get something like a rainbow where we can split and see the different colors. The rainbow of colors is called a continuous spectrum. I want you to bubble this in. continuous spectrum. Okay, and in the laboratory, we can use a prism or a diffraction device to bend light, causing the light to separate into what are called the component colors. Each color observed corresponds to specific waves of light. In this demonstration, we're going to look at white light through diffraction glasses. So these glasses that we're going to use are called diffraction glasses. And we'll then look at the light produced when electricity is passed through an element in the gas phase. So what we're actually going to do is we're going to take a power source and we are going to pass light through. I've got some tubes of different gases, and we're going to pass light through these to try to get an idea of what colors we can see. And I'll give you some information about how cool this is with the atoms. Okay, so what are some of the things that we're going to be talking about? So where do electrons live? So where are the electrons? Kind of reviewing some of the stuff that we talked about at the beginning of the semester. What happens when electrons leave what we're calling home, or where they originally were? What happens when electrons return home? They're going to come back. How do electromagnetic radiation, or how does it behave? And what is light, and what is a photon? So those are some of the things that we're going to end up talking about here. Okay, so we're going to draw and label the basic materials for the demonstration here. And so what we're going to do is we're going to start off by drawing this right here. And this is called the power source. Okay, so this here is the power source. I'm going to show you them first in the video, and then I will go back to normal. So this is going to be the power source. This is going to be our diffraction tube, our gas diffraction tube that we're going to end up drawing. And then we have our glasses. We've got the glasses, and that's pretty much it. And this does have to plug in, so we've got have to find an outlet to plug this into. All right, so let's go ahead and draw these out. I'm going to pause for a second while we get our drawings going, and then we'll come back and restart the video. Here's a drawing of our power source. It does have some electrodes in there, and then it does have to hook into some electrical. We've got an electrical outlet that we need to make sure that we plug this into. All right. The diffraction gratings, and so these are with the slits, and so that's the part of like the glasses here. So if you want to go ahead and draw those out. We've got the gas discharge tubes, and so there could be different elements inside of these. There could be it could just be one element, or it could be a mixture of elements. So you could have air, you could have just nitrogen, you could have oxygen, you could have neon. So like this one happens to be helium, the one that I grabbed, and I also grabbed an argon. So I got a couple noble gases. So I got helium and I got argon. Okay, so it says put the glasses on. And so what we're going to do is we're going to put these glasses on, and these are the diffraction gratings. What colors do you see starting with red? So after red, what do you see? Oh, you should see an orange. So we should see red. Yep. Red, orange. Do you see yellow? Yes. Now, it depends on where you're looking, but I'm definitely seeing yellow. Then what? Green. Good. What are you noticing? It's in the order of what? Yes, it's in the order of the rainbow. Yellow, green, blue, and then violet. So they don't call it purple. They usually will call it violet. Okay? And indigo was gone. So these are the colors of the rainbow. Colors of the rainbow. And so if you remember the Roy G. Biv. Okay, so those are going to be the colors of the rainbow. What are the glasses doing to the lights? What do we think that they're doing to the light? They're separating the light, so the slits separate the light into, anybody want to guess? There's a C word that I want to use. Into its what? What colors? Component colors. So if you look up here, it'll say like when we said into the component colors up there. So we were talking about the component colors, the colors that make it up. Okay. What happens if we turn the lights off? When we turn the lights off, did you see the colors anymore? No. No light, no colors. No lights equals no colors. Which means we actually need to supply what in order to be able to see the colors? We need, but in order to see the light, what do we need? We need energy. We need electricity. So we need energy slash electricity to see the light. Okay, this means in order to see the colors, we need to supply, what did we say? Energy or electricity. Light is a form of blank in the electromagnetic spectrum called something. Light is a form of, we call all of these, it starts with an R, we call all these different forms of, starts with an R, so yes, beautiful, radiation. Light is a form of radiation. So if you've heard before where they say there's ultraviolet radiation, be careful when you go out into the sun, you should wear sunscreen, perfect, to keep that radiation from going through. When you go to the dentist's office and you get an x-ray, you wear a lead vest to what? To block the radiation. Yes. So that radiation can be damaging. In the electromagnetic spectrum, where do we find, or what do you think that V was for in the electromagnetic spectrum? So it went radio, microwaves, infrared, something where Roy G. Biv was, and then it continued with ultraviolet. What do you think the V was for, everybody? Visible. Perfect. That's going to be the visible light part of the spectrum. Very good. So that is called visible light. White light is also called a continuous spectrum. And there's a reason why. It's called a continuous spectrum. Why do you think it's called continuous? What does continuous mean? Yep, it doesn't stop. It keeps on going because we actually see every single color in the rainbow. That's why they call it continuous. We see every color in the rainbow, meaning all frequencies of light are actually emitted. All frequencies of visible light are emitted. And that's kind of an important thing because right now what we're going to do is we're going to actually talk about the atom and what happens with the atom. Okay, so the atomic emission spectrum is a unique pattern of lines that form when electrons are going to be emitting energy at different frequencies. And so it says after electricity is passed through, and then we take a look through our diffraction gratings or through the prism, then we'll actually see different colors. Now with white light, which we're just looking at the imperfect, but the fluorescent lights up there, we see a continuous spectrum. So what we're going to do is we're going to draw what we see. Now I'm seeing it in the shape of like a rectangle when I look at one of our rectangle lights. And so I'm just going to kind of draw let me get, I guess it doesn't really matter what color we use as like our outside. So I'm going to do something like this. And then what I'm going to do is I'm going to draw the different layers. And what I see is kind of like the red. So when I look at it, I see red on the edges, and then it kind of goes orange, yellow, green, blue, purple, and it starts to overlap a little bit, but that's kind of what we're seeing here. Okay, so I'm going to pause, and we're going to put the colors in. And so I'm going to kind of start off with the red on the edge here. So I'm going to start off with the red on the edge, and then I'm going to continue on and get the different colors going inside of there. I'm just going to overlap them. So I know this isn't super clear, but I kind of wanted you to get an idea of what it looks like through the glasses. And so you can see with the light where you've got like the different colors of the rainbow. And so that's basically what we're taking a look at here. What I'm going to do now is I'm going to plug this in. And so I've got hydrogen. So I've already put hydrogen inside of here. Now, when I do turn this on, you're going to see a certain color that the hydrogen is actually going to give off. This might be, sorry. I just got it working. I've got hydrogen here, so what I'm going to do is I'm going to pop it right into here, into this slot. Now when I turn it on, what we're going to end up seeing, there's a violet color, but that's not what we're going to be really looking at. Okay, so I'm going to turn the lights off, and then we're going to see what we can, if we can see this. This is a spectrum chart, and I want to show you what you should see when you're looking at hydrogen. So when you're looking at hydrogen, so this actually here is hydrogen. Sorry, this is, let me come back this way. This is hydrogen, and so you should see a red band, and then you should see a blue band, and then something in the violet region. We really don't see many of the other colors when we're looking at hydrogen. So let's see what we can see. I just want you to see, this is kind of what we're seeing through the glasses. So you can see a red and a blue, and there should be a violet, but not really much more. So to kind of give you an idea of what we're seeing with the glasses here. All right. Okay, so this is what hydrogen's fingerprint actually looks like. So we can see the red. There should be something in like more of like the turquoisey range, blue and purple. Now what I saw was what I ended up drawing was something more like this. So I kind of did a pencil background and then red, blue, and a couple violets. It doesn't have to be perfect, but if you want to draw something like that. Next, what we're going to do is we're going to take a look at neon, and I think we should be good if we take a look at neon. I've got a couple more, but once you see one, you kind of get the idea of how these are. But this is a set, which is kind of cool. It does have a fingerprint. So this is one set fingerprint, which is pretty cool. So I'm just going to write that this is a fingerprint for hydrogen. Okay, and so when you go out into space, when we have, for example, telescopes, and we bring back the information, we could figure out what elements. So if you've ever wondered, like, how do they know what elements are on the sun if we can't get to the sun? So what we can do is we can bring back that data and just try to match it and say, oh, I see hydrogen, or I see helium. And so that's how they end up matching it to the fingerprints. And red isn't always, so like, this red here in hydrogen could be a different red from what is in helium or what is in carbon or something like that. So that red is a different frequency for a different element. All right, so we're going to take a look and see now what neon looks like. Okay, so I actually had to do helium instead because the neon's not working, but we should see a red band, a yellowish band, and then some of the blues. So that's what we're getting from this one here. This is helium, but this is helium backwards. So we should have seen a red, something in like the orangish, but that's that heavy gold color that we saw. And then green, and then a couple other colors here. So we're going to try to draw this. I am going to reverse it. So I like to do it in order of increasing frequency. So I like to start at the red, which is lower frequency, and then head toward kind of the bluish range. This is what we wrote down for the helium. Again, we crossed off neon, and then this one is extra here. So how are the atomic emission, and by the way, they are called either atomic emission spectra or a spectrum, one spectrum. How are they different from a continuous spectrum? What would you say was different about them? With the continuous, we saw every single color of the rainbow. Now we're only seeing specific patterns. So if an element has a set pattern of colors, or what we call frequencies of light. Frequencies of light emitted. Whereas in white light, you get all colors. White, continuous light, white, continuous equals all colors. So that's how they're different from each other. So with white light, we get all the colors, but if it's an element, you're only going to get one specific frequency of light. Okay, so let's talk about what's happening to these atoms, okay? All right, so we know that the atoms have different levels of the electrons. And what happens is these electrons are actually going to jump from one level to the next level when they absorb energy. And so what I would say that this is similar to is if I were to jump up to one higher level here, and then if I get up to another higher level here, but what's wrong with me? There's a U word that somebody might use. I'm a little bit unstable. Unstable is what they call, they say that the electrons, it's unstable at this high of a level. So I gained energy to actually come up here, okay? What's going to happen is I'm going to fall back down. Anybody want to guess what happens when I fall back down? I release energy. That's when you see the different colors of light. And depending on whether I bounce back to this level or if I actually bounce back down all the way down, that's a different packet of energy. Every single packet is called, anybody want to guess? It starts with a Q. It's called starts with a Q. Anybody think of a science word that starts with a Q that you want to guess at? It's called everybody say quantum. A quantum of energy. If you've ever heard that before, a quantum leap. So that's one packet of energy, and every packet actually equals one color of light or one type of radiation. It could be any radiation. It could be an X-ray, it could be gamma, or it could be a radio wave. All right. So basically what happens is it's almost like being on a sugar high. You take the energy in, that's the power source that supplies the energy to the atoms. The atoms absorb the energy, they become excited, and they jump up to higher levels. But like we said, number 3, at those higher levels, those electrons are unstable. So what happens is they fall back down toward the nucleus, and they could fall back down at different levels. And every single packet that's released is called a quantum. But quanta would be plural, or a photon of energy, and each color equals 1 frequency of radiation, but it could be radio waves and it could be gamma waves. So it could be a wave that produces music for our ears, or it could actually be a wave that could kill us, like the gamma radiation would. All right, and the last questions here, we're going to talk about, do all gases, gaseous elements have the same spectra? The answer is no, they do not. Each one has its own fingerprint. And what does this mean? Each element releases a certain packet of energy, releases different packets of energy, different packets of energy. So they each have their own basic pattern. So each one will have their own pattern. A different pattern for each one. So stars are made of, are hot bodies of gas. How do we know that? How do we know which gases stars are made of? We use, starts with a T. What's the instrument that we use? We use telescopes. We use telescopes to basically gather the information, gather the data or the information with the patterns. And then we identify, we basically match up those patterns to a certain element. Those patterns are matched with the elements that we have found here. 2 elements we already know. All right, I hope that you learned a little bit more about light and how light works and the fact that it's a form of radiation, because a lot of people don't know that. And so, and hopefully you got some good learning from this Bohr light demo. Happy day, everyone.